to start off, let's go around and have a quick intro. And we'll have a group of really esteemed panelists today, experts all around CK, cryptography, hardware, and so yeah, let's start with you, Bayan. Tell us a bit about yourself and answer a question, which is what excites you the most about the intersection between cryptography and hardware?
Uh, hi, I'm Bang Yan. I'm from Cysic. A general hardware company that is designing general ZK acceleration hardware. Basically the competitor of Fabric. So, hi. So if you're asking what's the most exciting interaction, basically I'm so I graduated from my PhD thesis is about hardware acceleration. So for me, like designing a new hardware that is kind of competing with NVIDIA is simply the most exciting thing for us. But like for me personally, uh, zero knowledge proof is really a new um, kind of workload that is so promising. So uh, so it's kind of a totally new workload. It just like the AI several years ago. Not just prime field computation. You can look at a lot of like cryptographic construction. So by examining that and designing uh, hardware to handle that kind of workload is kind of puzzle solving because you need to come up with some kind of new hardware construction to map those algorithms. So
Definitely a lot of hard problems. So we can dive into details in this panel. We'll have 40 minutes. So let's go to Brian next.
Yeah, I'm Brian Retford, CEO at RiscZero. We're mostly a software company at this point. We design general purpose zero knowledge ZK VMs. So we're obviously looking to this whole hardware space to help get our technology into more use cases and more niches. And I think that is, in fact, the thing I'm most excited about. And that's that every time you 10x or 100x the performance or performance per watt, really. So you could drive power down or you could drive performance up. You open up a whole lot of new use cases. And so, yeah, I'm excited to see ZK hardware bring ZK into everybody's phone in 5 to 10 years, and into IoT devices, and really, yeah, transform how we own our own digital footprint.
Hey, I'm Michael. I'm the CEO of Fabric Cryptography, and we're building the processor that Dave was just talking about on stage, the VPU, the Verifiable Processing Unit, a general purpose processor to accelerate cryptography by orders of magnitude. And the reason I'm really excited, it's not about the hardware for me, it's about the mission. I've been in AI hardware in my previous company, and we were selling to just 5 customers. And those 5 customers had effective control of the entire AI landscape. And what I'm really excited about is these cryptographic constructions, not just ZK, but also FHE and all these new constructions, are going to liberate us from that oligopoly. And they're going to let everyone own their data. And they're going to solve these privacy and trust problems that have been brewing in society for decades. And so what I'm excited about is making these technologies ubiquitous and powering everything in the world.
Herbert.
Yeah, Herbert Chang. I'm actually a venture capitalist and invest in semiconductor in the last 30 years. I work with TSMC and helping numerous early stage semiconductor company become a semiconductor giant right now, like a Marvell Semiconductor, monolithic power system, L-chip technology, and a lot of companies like that. I've been seeing semiconductor is something behind lots of the great story, but nobody really pay attention to it. And recently, I switched my focus on how to use semiconductor to help the ZKP become more feasible and also cost effective.
So Herbert, perhaps let us really pick your brain on your 30 years of experience here. What would you recommend for a new area of computing to think about in terms of chip design? So yesterday when we were chatting, you told me that we should change the title of the panel from ASICs to chips. So yeah, maybe tell us more about that and what your recommendation is.
When I get in touch with the ZKP ecosystem, and quickly the first things I found out is, the whole semiconductor industry actually have zero knowledge about what is a ZKP. And same thing, the most of the people in the ZK ecosystem, you guys don't know what is a semiconductor at all. So let me tell you, semiconductor is 5 years ago nobody know what is the AI. So, but AI actually, the AI things have been around almost 40 years. When I studied in the graduate school, it's actually I studied AI at that time, but it's not feasible at all because it's too slow. You have no way to do the real AI calculation. And thanks for the Jason Huang, he started 10 years ago thinking about how semiconductor can help AI calculation, speed up. And based on his claim, in the last 10 years, he speed up 1 million times for any AI calculation. That's make the AI become feasible and now gradually create an ecosystem. But based on the semiconductor, there's a numerous approach to speed up the transaction. The first thing is the architecture of the chip design, like David just mentioned. Different architecture will have totally different effect. So it's not just you go the deeper submicron. It's not that. The first thing is the architecture. So the GPU is not good for ZK proof actually. So it's too slow. It's same thing. The CPU is not fast enough for the AI calculation. So you need something unique. But at this stage, it's still too early stage to using something like ASIC, because ASIC is everything fixed. So maybe 5 years down the road, 10 years down the road, we have an ASIC for something like a portable ZK proofs device. That's feasible. But now at this moment, I think the most important thing is use the semiconductor technology, make the ZK proof is cost effective and fast enough, so that you can help the whole industry grow really fast.
So it sounds like the recommendation is don't go to fixed circuit ASICs.
It's just too early.
Yeah, let's turn this question to Michael and Banyan here, since you two are from the two companies that I know of that's really taping out chips today. Would you call your product a fixed circuit ASIC, or is it more programmable? Michael first.
Yeah, thank you, Wei. I would certainly not say that we're fixed function. It's much more like a GPU built for cryptography than it is a fixed function ASIC. There was a famous post that came out about ASICs and cryptography a while ago that talked about, hey, like an ASIC becomes a paperweight effectively once the algorithms change, and that's something that Dave was talking about in his talk. And that's something that we really believe to our core. There were a lot of AI chips. I used to be in AI hardware. There were a lot of AI chips that died because they didn't follow the industry. When the industry shifted from image models to language models, the same chips couldn't run it. And so, what we're focused on is creating that blank canvas for general purpose computing of cryptography, right? We've broken down cryptography into the primitives, and we're really building a domain-specific accelerator and not an ASIC. And so that's kind of like a technical term for what we're building.
Great. What about Cysic?
Well, so I would say we have a good support on the general purpose part, but we also have kind of specialized part. So the thing is for all the workload in ZK, you can divide them into two categories. One category is basically something that is designed to be random. For example, hash function. Well, there is not a very clear rule on how a hash function should be defined. So things might be changed throughout the time. For example, in the past, people use star, and then people switch to, for example, prime field based, for example, Goldilocks kind of operations. So for that part, we must have general purpose and programmable processors. But on the other hand, you have some kind of operation that is fixed because it's defined by mass and it will not be changed in the future. For example, elliptic graph curve operations, for group add, it have to be in this form because as soon as the curve is defined, then the operation cannot be changed in the future. So for that type of operation, you can spend a little amount of resource to develop hardwired connections. I would say we are not going to design fully hardwired component, but like some extra control wires to make them more efficient. So I would say make general purpose as efficient as possible, but for those that is known that we know that it will be fixed for a long time, we should spend some kind of extra resource to make them more efficient.
Can I actually ask both of them a question, and then I'll go to Brian. Sorry, this is too interesting for me to pass up here. So, Ben, you mentioned cryptography might not change for a long time, and is this something that what we have seen like fields change, right? Actually, maybe I should go to Brian. Brian, do you have a comment on like will cryptography change?
Yeah, I mean, I don't have any reason to believe that it's not going to. If you look at the papers that are coming out, how dramatically, who knows? But I think when you look at putting an entire proof system on a chip, NTTs are a huge part of our protocol, but so is evaluating polynomials across a vast number of points. And you can imagine even the way you construct your memory arguments changing the sort of exact like optimal way to flow memory through a chip. So I'll just say in my time at Intel, I saw people move from sort of like AI chips that had a bunch of fixed function units tied into something that only did convolutions. And then the day LSTMs came out, people were like, they couldn't support their customers anymore. So I tend to have a bias towards flexibility where possible, but there's a cost for sure.
Right, follow up. Do you think, so you guys are currently using this 31-bit baby bear field. Sorry, we're gonna get a little bit technical here and into the weeds. Are you guys planning on changing to a different field?
We're trying to design a proof system that can operate in multiple fields easily. I think Plonky 3 is a little more flexible than us right now on that front. But yeah, so far we haven't seen any reason to switch yet, although, Fabric's chips work better with 64 bits. So we actually want to get to the place where we're defining our circuits in a way that is as field neutral as possible so that we can target whatever hardware devices come up and whatever new fields people decide are most optimal, including like Binius, which is a completely different paradigm, right?
Yeah, this makes a lot of sense. So, Michael, just really quickly, can you tell us kind of, is there any fixed functionalities on the V1 VPU that you made the conscious decision to actually fix because you see the demand for?
Yeah, sure. I'm going to answer that in two ways. One way is how much area, how much silicon resources is spent on fixed function units, and to that I would say very little. We spend a little bit of area supporting stuff like hard-coded Goldilocks operations because Goldilocks is in common use and because that doesn't cost too much area. But for the vast majority of the chip, it's basically general purpose. And then another way of answering that is we have the philosophy that, over 90% of our area, over probably 95% of our area should always be spent on resources that can be used by any computation. And there's a very specific reason that we make that trade-off. And it's because, if you look at NVIDIA and you look at history, NVIDIA released a revolutionary GPU architecture in 2006 called Tesla, right? It's famous in the computer architecture world. And what Tesla introduced was, before Tesla, even NVIDIA's own chips had hard-coded shader pipelines that worked a certain way. And there was a limited degree of programmability, but everyone made the assumption, hey, everyone needs shading. This is the way shading works. We're going to support this limited range of shading. And what NVIDIA consciously chose to do in 2006 that launched them into the stratosphere being a $1 trillion company is they decided to move away from that. And this was very controversial within the company at the time. They chose to make a large ocean of homogeneous SMs, streaming multiprocessors. And basically all these things did was they did floating point compute, and that's all they did. And so what's really cool is over the next 20 years, you can see that NVIDIA became a powerhouse that it is today based on CUDA. And CUDA could only really exist with truly general purpose chips. So, just looking at that success story, looking at some of these AI chip startups that didn't do so well, we're learning that lesson. We're being a general purpose company basically forever. And we believe that that's the best for the ecosystem as well, to democratize these constructs, to allow people to iterate on them, and to make that blank canvas for cryptography research.
Okay. Thanks, Michael, for the detailed answer. So, if I may, I think the answer I was looking for is actually like quite simple, which is that there was a choice made in the V1 design where this very, very widely used field called Goldilocks is actually fixed in the VPU, right? Is that correct, Michael?
Yeah, that's right. And so there's a very specific reason to do that, right? So if you look at Barrett reduction takes 3 cycles, right? So if you want to do a modular multiplication with a Barrett reduction, you have to do 3 steps, or 2.5, call it. If you want to mod out by Goldilocks, it's much simpler because it's 2 to the 64 minus 2 to the 32 plus 1. You can do some shifts, you can do some adds, which are relatively cheap in circuitry terms, and you can just mod out in 1 step. And so what we chose to do is, because the overhead is so small, okay, we're going to hard code that in as an option, and if people don't use it, it doesn't lead to that much dead silicon. So it's always a trade-off in this like hardware-software co-design process. You're looking at the workloads and you're thinking, okay, do I support this long tail feature or not? And you're thinking about cost-benefit. And the cost is small, the benefit's huge. Okay, like you do it.
Okay, so I guess to wrap up this round of discussion, it sounds like we need general purpose chips that we can program, but we need to fix certain functionality that's used across our computation. If one day we all fix a field, maybe Baby Bear or Goldilocks will fix that in the circuit, but probably not, it sounds like. Okay, so let's actually move to more forward-facing discussions here, which I think it's what I'm really excited for. Banyan, what is like? What do you think is going to be the kind of future of hardware? Like, if you look 5-10 years down the line, if you see Cysic making a chip, what features would it have? Does that make sense?
What future?
Yes. So, if looking 5-10 years down the line, as the hardware that you design iterates, what is the features that you think? Okay, so I guess I'm alluding to, for example, real-time ZK, right? Or for example, like getting the cost of compute as low as possible. Is that so? Yeah. What excites you about the next couple iterations of Cysic's hardware?
Well, so I would say within the 5 years, the more popular way of designing hardware would be a kind of acceleration card, just like how GPU works. You will have a host CPU, and you will have your acceleration card integrated to the host system via PCI extension, so that like your CPU offload the proof task to your acceleration card. But I would say, I believe in the 5 or 10 years, people might prefer to switch to a kind of end-to-end acceleration hardware, where most of the computation can be directly performed in like the accelerator card itself. The reason for that is like end-to-end. In order to achieve really good end-to-end acceleration, you need to take care of all the computation time plus the transmission time. And we know like currently most Vitless generation stuff are performed on host CPU, and they generate a huge data which have to be transmitted to the acceleration card, which is quite often to become the hardware bottleneck. But that takes time to build a hardware system that can do everything at once. We can integrate some CPU cores in our accelerator card, but currently there's still too many operations that have to rely on host CPU, like 4 or 8, like for example, RISC-V or ARM core is just not enough. But I would say like 5 to 10 years later, the algorithm itself is more matured. Then we can look at the detail and the design, like better solution to fit that.
Okay. So Herbert, so in your we have seen a lot of process node changes, right, over the years, and we're down to now like 3 nanometers. In the next 5 to 10 years, what do you see as the trajectory of process nodes?
I think in the semis world, there's a various way you can really achieve performance. But other than the performance, the other thing is very important for the whole ecosystem development is the cost. So this is something you need to justify, cost and the performance. Thanks for the semiconductor process migration, so you can make the performance easier than before. But the cost is different. The most advanced technology you use will be cost you a lot. And the cost is two-way. One is per chip cost. The other is the development cost. So say right now, if you want to do something like a 3 nanometer, 2 nanometer, you're talking about $50 million for just a tape out. not even mention about the development cost. So basically what I believe is in 5-10 years down the road, if we really want to make the proof cost effective and fast enough, so it's involved with semiconductor and as well as software. This is very different with all other semiconductor project I involved. Those are very specific, and you don't not a lot of software stuff involved. But ZK proof is totally different. Yeah, you have all different kinds of proof, this and that. So I believe whoever want to do a good semiconductor and make a lot of the contribution, software is another dimension you need to think about. Yeah, so it's not like okay, we have a chip and I give it to you guys, you can use it. It's not like the case. Yeah, so whoever can have the whole system is just like a end-to-end proof. That's very important to help the industry.
Got it. So it's not just process nodes; it's the whole process. Brian, next 5 to 10 years predictions.
Yeah. Predictions. I have my things that I hope happen, and I'll just go over those. What I really like to see is a piece of hardware come out that actually supports a proof system that I still haven't seen, that produces like lower security proofs extraordinarily quickly, so you can do like ZK flash bots effectively and other kinds of blind auctions. I just think that would be really interesting. And I also think that there's a lot of utility in those kind of systems for sort of defense in depth in a highly IoT-ified world. But from RiscZero's perspective, it'd just be great to have the absolute fastest and lowest like tops per watt card we possibly could have. So hopefully we get some of each of those.
Michael.
Yeah, I'm excited about this one. So in the 5-year timeline, what I really see in terms of ZK hardware, it's like Herbert said, it's not just about radically better performance. Probably 5 years from now, we'll probably be on 2 nanometer. We'll be on Gen 4. It'll be super fast. It'll be orders of magnitude even beyond our V1 product. So I'm super excited about that. But even more exciting is the programmability aspect, and that's not just the hardware; it's the software layer on top. I think Dennis from Matter Labs gave a great presentation on formal verification of ZK circuits. And what I really want to do is shorten the distance as much as possible between LaTeX, writing an equation, and low-level assembly. And I think like one day we're going to have not just ZK hardware, but ZK software that is co-integrated with it that's so good that it's, to the point of insanely good, and you can write just an equation and it transpiles the rest. So that's one really exciting thing. Now, in terms of like the 10-year timeline, I think that where we really see the field of ZK processors going is it's going to be all over the place. It's not just going to be in data centers. It's not just going to be a PCIe card that you plug into your consumer PC. But what we hope is that it's going to proliferate. You're going to have VPUs in your phone. You're going to have VPUs in your pocket. You have VPUs for ZK middle boxes for routers, that Cisco is pumping out in the millions, right? ZK should be everywhere, because the privacy versus trust trade-off should be eliminated from every place. And so we hope to make that ubiquitous.
Yep. Very well said.
So yeah, perhaps let's explore those different use cases, right? I think in all of those use cases you just mentioned, Michael, there's no rollouts being mentioned, and that's probably the largest use case today. So Brian, maybe like enlighten us. What other use cases are there for cryptographic hardware?
Well, I mean, certainly, you mean outside of rollups or inside of rollups? I mean, I would say like if you look at a large number of the partners we're working with right now, they are all trying to build roll-ups or roll-apps or effectively order books, things like this. They want to build them completely in ZK, and we've made it possible for them to build something in ZK, but we still find that running all of an optimism chain in pure ZK, we still need like a 50x reduction in cost, and I think it would be better if it were even more than that. So the application for ZK hardware inside rollups is going to be, I think, really like salient. I think a lot of people are moving to these kind of like ZK fraud-proof stake systems as a temporary compromise, and they're just waiting for the sort of raw horsepower to be there.
Actually, this is a good point. So maybe let me set the context a little bit. So there's the overhead of cost in ZK, and there's the overhead in time of ZK, right? One is typically a lot larger than the other, and maybe let's go around the panel and ask what the prediction that you think, for the cost overhead for ZK and the time delay overhead for ZK. Herbert.
I think the key is the cost to make it affordable. So performance, I don't really worry about that. Based on today's technology, if you don't care about cost, that's easy. Yeah, but the problem is if you really want to make an industry grow, you need to make it affordable and feasible. So I would say, hey, the performance probably not an issue, yeah, but the cost. Yeah, so how to make it really affordable to everyone.
Michael?
And perhaps I'll put some numbers on it. Right now, that the state of the art for kappa, which is Wei coined this wonderful term called kappa. It's the overhead of a ZK proof of a computation versus running the computation itself. And the overhead currently sits at, I think, roughly like 10 to the 4, 10 to the 5, something like that. And so, there are a few components of that, and part of it is the lack of dedicated hardware. And what we think is that dedicated hardware is going to, bring that down by probably around the hundreds of X to 1000X kind of range. Like, we actually think that, when you put our architecture on 3 nanometer, when you overclock it, when you pipeline it to the max, and when you actually max out the capabilities of things like full custom design, there's a lot of room. We're going to, take this to the stratosphere. And then the other aspect of it is embedding overhead. And what I see these days is a lot of wonderful research on embedding overhead. And I think the combination of that and hardware is going to drive it closer and closer to native cost. And so while I'm a little hesitant to put a concrete number on the combination of those, because it doesn't always multiplicatively neatly stack, I think there's a world where we could see under 100x. And I think that's pretty exciting.
Do you believe that's going to be correct? Like under 100x, Brian, do you think that's something achievable in the next 5 to 10 years?
On a cost basis, yeah, but not necessarily on a performance basis. I guess
cost.
Yeah. So, and I do think that I'm certain, both from my experience at Google Cloud and from just what we've learned being out in the marketplace, that there will be demand for different sort of SLA tiers, and people might, there might be some applications where you absolutely need, a proof generated every 500 milliseconds, plus or minus 10 milliseconds, and there also might be people who are trying to do like bulk ZKML training, and they don't care if their job finishes a week from now, and that can run on random people's GPUs. So I expect we'll actually see a spectrum there, and I think we just have to look at the proliferation of all of the different machine and node types on Amazon to see people will, optimize as much as they can.
So what is your prediction of that number? What is your prediction of kappa? 10 years.
Yeah, I mean, it's just cost. It seems like, were you saying below 100? Yeah, I think below 100 for sure. 10. Let's say 10.
And something that's too juicy to pass up talking about is the potential for specialized proof systems like ZKML to drive that even lower. And so I think that's pretty.
Let's save that for just a minute. Diane, what do you think the general kappa will be in 5 to 10 year time horizon? Yeah.
So cost.
Yes. So cost overheads.
Yeah. So because like there's 2 types of cost. I totally agree that like the proof cost will be reduced significantly with the availability of ZK hardware together with the algorithm development. But like in terms of like software development cost, which like the difficulty to build up software ZK proof system, I would say with the introduce of ZK hardware, it might initially increase a little bit, but in the long term it will be reduced. Why? Because like with more different hardware available in the market, like you have to kind of integration problems. Just imagine like a CPU only proof system and a GPU compatible. So yeah, software effort is not the cost paid by the end user. It's just the development. But I like with the help of like SDK provided by the hardware company, and I wish that in the long-term future we will have our community will have something like PyTorch for AI, where people you have a uniform interface that everyone can write their proof system in a like basically the same style, even though their low-level design might be different, but like using the same interface, like every hardware can only need to like support that kind of so-called PyTorch for ZK, and then all the top level like software developer can only need to write their proof system using that interface. That will finally reduce the cost.
It's like the cost of development, right?
Yeah, development.
But
yeah, so
what's your prediction of the cost of like actual running the proving?
Yeah, like yeah, it will be reduced like but like how many magnitude it's hard to predict in 5 years. Like no.
Give a bold prediction. We're not keep you on hook.
Well, like I wish to say like 2 magnitude.
So if you're currently at 4, you also think 100 basically.
Yeah.
Okay. And Herbert, we didn't get a concrete answer from you. Do you think it was 100, less than 110?
I think less than 100 is very doable, yeah.
Looks like we'll have a consensus here. It's like I think everybody is saying it's less than 100 and maybe somewhere around 10. I guess we'll check back in 5 to 10 years to see whether we get there. So, but that means basically ZK is gonna take over like the optimistic solutions, right? Because optimistic solutions will need to run at least like around dozen nodes, and that's a factor of 10. Yeah, so perhaps let's open up the panel to the audience. Do you guys want to do that? Raise your hand if you have a question. Roddy.
Hey guys, we saw a really cool demo by RiscZero running Doom, so I guess now you're officially a computer. And if I'm not wrong, Brian, that was like 3.7 megahertz of virtual clock speed. So my question is like, sorry, what would be the speed up by these hardware devices for example, running Doom? And can we see the multiplayer mode with RiscZero perhaps later this year? Thank you.
Yeah, so the bottlenecks in that particular 4.7 megahertz are actually like have to do with witness generation and sort of simulation. Now there are things that we can do. We expect to see a 5 to 10x increase just in fixing cruft that we have left lying around. That said, as soon as we actually get past that, and then we really are able to utilize these kinds of systems, will still be, to some extent, for something like Doom that's single-threaded, limited by the single core speed at which you can simulate a RISC-V instruction set with all the necessary instrumentation to then prove in parallel. But I honestly think that we could see hundreds of megahertz by the end of the year, and maybe line level in 2 years. Maybe.
I actually want to expand on this question maybe to also like the two chip makers here. Yeah, what do you think? So it sounds like VPU already has witness generation on chip, right? Meaning that you can like really custom design it. And Cysic currently does not have that. Like, yeah, what is your prediction if you run RiscZero on your chip? What is the megahertz and the trajectory of that, going forward?
Yeah, this is exciting. So, there's the instrumentation itself. I think that part is a comparatively small percentage of the total runtime. And then there's like the actual act of expanding the witness. And the witness expansion for RiscZero, we actually profiled it on our instruction set. So we kind of split that whole task of generating, the final trace table that's the input to the proof system between our RISC-V processor and our tiles. And the combined speed up there, I think should be over an order of magnitude, which is pretty exciting. So I
So
think
like
that we will
50
see this.
megahertz. If you
Well,
do it right now.
hopefully he gets rid of the cruft at the same time, and we can, really have some smashing records.
Yeah.
Diane.
We currently don't have that kind of number.
Let's sort of. Yeah. Any more questions from the audience?
Great panel. This was one of the best panels I've been to all year, so awesome. Since you guys were talking a little bit about blue sky, 5 to 10 years, how do you think ZK will impact consumer-grade hardware devices, like things like phones, laptops? Like, is it possible to unbundle the operators or the producers of these devices from the devices themselves, because now we're optimizing for different things and everybody's using ZK, so we can kind of start to democratize these types of devices a little bit? I know it's blue sky.
That's actually exactly what our long-term roadmap actually entails, because the number one thing is there's all this spare capacity of compute at home. And what's really interesting to us is if specialized proof systems, we can drive kappa down so low that decentralized depins become much more possible, then we're going to be able to actually not just monetize that capacity, we're also going to be able to drive VPUs into consumer devices a lot more feasibly from a financial perspective. And what that means is, these token incentivized VPUs being in everyone's, computers or phones or whatever, that's a very compelling future, because suddenly everyone has access to privacy at the same time, right? So hopefully we have some combination of moves that us and other players in the ecosystem are able to make, such that we end up in a future where everyone has a VPU. And I really want that for humanity.
Yeah, I think that the ZK HSM, you've seen hardware security modules on phones really start to take off recently, and it's honestly helping out the crypto onboarding experience immensely. But at the end of the day, there's still a lot of trust assumptions baked into those particular systems. So I think alongside these kind of trusted components that have basically fundamental security flaws, and you have to be very careful in how you use them, with something that is more trustless, more ZK, and can really enable this sort of attenuated identity and privacy that I think is going to be, and provenance as well. That's really going to be the hallmark of the next 10 years.
Actually, the beauty of the semiconductor is that you can scale up and also you can scale down. Okay, so you want a further performance enhancement, you can scale up if your architecture is good. And also if you want to be very cost effective and through a good way to partition the task into different places, then you can scale down and go down to your phone, even USB-based stuff. That's very doable.
Diane.
Oh, like I would say, the time to the day where almost every hardware, including every personal devices, include like kind of a ZK proof like processor inside the system, might be quick very soon or very quick. Just imagine like AI gets popular 10 years within, I would say 5 to 10 years ago, but like currently every smartphone have a AI acceleration unit inside it. So I would say it takes 10 years to.
I was going to say 10 years for sure.
All right, I think, okay, one quick question. I think maybe we'll give 30 seconds for the panelists.
Hey guys, thank you very much. Great panel, as everybody said. I'm just curious about what you think about the market in a few years, in the sense that I think it makes a lot of sense to put and to accelerate what we can do with ZK. ZK makes a lot of sense for many, many applications in the world. Right now, the crypto space is spearheading this research, but I think like just the general people and Web2 space is gonna catch up and find this hyper interesting. So I'm just curious with what we've seen with, for example, Apple making their chips in-house at one point because it made so much sense. Do you think that general companies for like Fabric or Cysic, if like companies like Apple will not make their own chips in-house for ZK, and then all these companies will make their own chips? So just curious about how do you think about the future of your companies compared to these enormous giants?
Quick 20-second answers.
I think the crypto space is pretty big, and we want to be a champion of the values and the decentralized ethos of crypto. And so we would hope to be independent. And we have a business plan that I think is going to get us there because the market size I see is really, really huge.
You also have to remember that, ARM, extraordinarily valuable company that's, in most of our phones in this room, they sell their IP, and this is very common in the semiconductor industry. So it's entirely possible that, the IP that any of these teams develop could end up being licensed inside a particular chip. I think, based on my time at Intel, it's just a strategic decision as to whether they want to try to in-house it or buy some IP.
Oh, well, I would say, let's just forget about Apple. Well, Apple used to buy some kind of graphic card from outside, but currently they are designing everything from their in-house design. So if they keep this trend, then they might be happy with them in-house TK design, hardware design. But yeah, but the biggest word
Unfortunately, I had to move. Herbert, any quick remarks from your side?
I give you a very simple answer. Any semiconductor development takes you at least 18 months to 24 months. So there will be a time lag. So someday, if these guys make ZK, very affordable, at that time, even a company like Apple, who else, found it out, it still take them at least 18 to 24 months. So it's too difficult to catch up. That's the reason why I invest in semiconductors for 30 years. Every time we invest in a new area, but at the same time, it's already a lot of the giant there. But how come I'm not afraid? It's simple, because they don't pay attention at the time. And later on, when they found it out, it's too late.
Okay. All right. That's all we have time for. We're running over. Thanks a lot. Thanks our panelists.
From 1KX, then Ahmed from Biconomy, John Ennis from Safe, and Adam from Alchemy.